Good morning. So we were doing our module 2 of our course, Vehicle Dynamics. In that module 2, we are learning vertical dynamics, otherwise called the ride dynamics. So in the last class, we just have started the module and we understood the importance of ride dynamics. It is especially the comfort of the occupant in a vehicle is concerned. The ride dynamics is very important. So the ride dynamics helps to model our vehicle, which is otherwise very complex structure, into finite number of degrees of freedom, and we are able to find out the response of the occupant or response at different locations in your vehicle for the various sources that can act on the vehicle. So major sources, the surface irregularities. Other sources are aerodynamic forces, vibration of engine and transmission, non-uniformities in tire wheel assembly, and so on. So these are all something that in the last class we just have looked at. And then we started with having three important objectives or parts of this ride dynamics that we are going to learn. One is first understanding vibration behavior of the vehicle with a simplified mathematical model. Another aspect is to understand human response to vibration. So there are standards that says that this is that allowable level of acceleration that occupant can be subjected to for a prolonged drive of a vehicle and so on. So such kind of standards is what we are going to look at it. And thirdly, we are going to look at characteristics of road surface irregularities. So what is the characteristics of the road surface? In real time, if you look at what is acting on the vehicle is the random excitation, whereas we are doing our vehicular mathematical model only with deterministic model. So harmonic excitation is what we are studying it. So I'm just going to start from where we left in the last class and continue our class, right? So let me share the screen. Are you able to see the board? No, this is not. So you're able to see this board. So look at in the last class, we are just doing this. We are going to continue with what we were doing in the last class. So a mathematical model is nothing but lumped mass spring damper model. So you could see here a 7-degree freedom ride model of a passenger car, which is called a full car model. Anyhow, we are not going to form the equation and do for a full car model, though that would give you more insight. You can also have a simplified model like a 2-degree freedom model, quarter car model, or pitch and bounce model. That's quite sufficient to understand an important rigid body modes of vibration of your vehicle body. So that's what we understood, and we started with this model. I just forgot my mouse today. We are going to continue from where we left, right? So I think we were into equation number 13 and 14. So if you look at any vibration analysis, we follow a certain sequence of looking at the analysis. So first step in any vibration analysis is model description. So we were able to take 1/4 of the vehicle model called the quarter car model, and where we defined sprung mass and an unsprung mass, and the road profile, varying profile like this. And we were able to apply Newton's second law and able to write the governing equation for sprung mass as well as an unsprung mass. And then we continued with these two equations, what we have derived further to find out in the third step the natural modes or amplitude ratios of free vibrational study. So what is that will do? When you say free vibrational study, it is basically not considering the damping in the system. It is only undamped free vibrational study. So you see here the same quarter car model can be expressed as only with the suspension spring and the equivalent tire stiffness. And then you had equation 3 and 4, and the trial solution is harmonic solution. So that is why it is called a deterministic model. What is this model called? A deterministic model. Deterministic model. So substituting this in this equation 3 and 4, I am able to write this form, equation 7 and 8, and then you see that for any values of Z1 and Z2, the equation 7 and 8 can be satisfied in the following determinant equating to 0, and that would give you what is called a characteristic equation of the system. So the equation 10 is what is called a characteristic equation, and the roots of this characteristic equation is going to give you what is called the natural frequencies of the quarter car model, and that is what is obtained from equation 11 and 12, where we define here for a compactness of the equation A1, B1, C1. So what are A1, B1, C1 that you know, and we have just written down from there. When I take this, I get two roots. There is no meaning for a negative sign. So we have neglected, and then we got into positive values of omega n1 and omega n2. So omega n1 refer to a natural frequency of sprung mass. Omega n2 is natural frequency of one unsprung mass. And you are given with this equation number 13 and 14 respectively. So this is where we just have stopped in the last class. I'm going to continue from here now. So what is that is, you can also make an approximation method, right? So what is that approximation method? Is this. So this is lecture number 13 and today's date 2021, right? The same model can be considered to be a 2 single degree freedom model. Why is it so? Because if you look at the default design of your vehicle, the mass of your body, if you look at mass of the unsprung body, they are very one order different. So if it is of some 1000 kg body mass, then it would be around 100 kgs only. The similar way, if you look at the stiffness of the suspension and stiffness of the tire, they are one order difference. So the tire stiffness is huge compared to that of the suspension stiffness. So this is going to give you the sort of approximation method also is possible. Instead of having quarter car model, you can approximately reduce that to a single degree freedom model, 2 single degree freedom model. So what is that we are going to do is, let's consider mass ms and the two springs, one is kt, and I am not going to consider now the unsprung mass, and instead I consider the tire stiffness ktr. So the mass is neglected here because it is one order less than that of sprung mass, and then I look at this as a mass and spring model, and this is going to be now single degree of freedom model. And you see there are two springs are in series, so I can find out what is called the equivalent stiffness of the spring, and that would be 1 plus kt. This is suspension. It's not kt. It is ks. So ks plus 1 by ktr. So that's going to give you what is k equivalent as ks ktr by ks plus ktr. So by having this, now I can find out what is my natural frequency of sprung mass. So that is going to be 2 pi by omega ns, and that's going to be 2 pi, sorry, 1 by omega 2 pi f is what is this? So please correct this. Omega n, yes, by 2 pi. And that's going to be 1 by 2 pi under root of k equivalent by ms. So that's going to be ks ktr by ms into ks plus ktr. Right, so you have this now, and you can substitute this value of the problem that we have seen in the last class. What was the problem? Just a minute, get that screen. Last class, we had for example, problem data is this. So you can have these data of the sprung mass, unsprung mass, and the stiffness of the spring in the suspension and tire stiffness. So take this value and find out your natural frequencies. In this case, they are no way going to be different from that of what you could find out from 2-degree freedom model from equation 13 and 14, where we stopped last lecture. So I can substitute this and find out the natural frequency of sprung mass. That would be almost equal to 1 hertz. And similarly, I can have the other mass, that is unsprung mass, and it is connected to sprung mass by ks and to the ground through tire wheel assembly, so that to take it is KTR. So if we take like this model, and this model is now mass and two springs are in parallel, so K equivalent in this case become KS plus KTR. So this we have already studied during strength of material course, or you can remember that when springs are in parallel and you have a mass, the equivalent stiffness get added. When springs are in series and you have to get equivalent stiffness, then this is the relationship that you should use, right? So please make a note of it. And now you would be able to get what is the natural frequency of an unsprung mass. That would be omega n us by 2 pi. So that's going to be 1 by 2 pi into ks plus ktr by mus. So by substituting that, you would be able to get this value. So this is permitted, or this is the design of your passenger car because of your body mass and the unsprung mass proportion and the stiffness of the suspension and the tire stiffness values, right? So this you should remember. And there are some important points that we will look at now, important understanding of this so far what we have done. And then we will go in for finding out what is the amplitude ratio for the given road input, right? So now if I have to find the amplitude ratio, it is Z1 by Z2, that is between your sprung mass and unsprung mass. But now what is that you have to understand is, here you would get this is approximately equal to 1 hertz, and this is approximately going to be equal to 10 hertz. So the ratio of frequency you see now, it is 10 by 1. So if I have my first model, case 1 here, the input to this model is coming from your unsprung mass. So if unsprung mass is excitation frequency is 10 hertz, and whereas the resonant frequency of sprung mass is 1 hertz, they are very well separated. That's going to give a very interesting insight that your unsprung mass act as an isolator for your passenger car. That's what you'll understand at the end of the lecture, even when you look at a pitch and bounce model in this class. So you see this is now well separated frequencies. So that is the reason why you can have such an approximation, and we have to follow some of the implication. So the amplitude ratio Z1 by Z2 can be obtained from equation number what we had in the last class, equation number 4 and 5, I think. So you can use that and you can find out. But this is not of our interest. What is our interest is what is that Z1 for the given road input excitation or the road profile Z0 or Z2 by Z0. So for that I have to extend my analysis looking at the equation further with the quarter car model, right? Again, going back to your 2-degree freedom model. So before that, let's make some of the interesting note. So note number 1 is the natural frequencies are commonly used to characterize the system that we know. So there is a very little difference between your damped and undamped natural frequency. So you have W omega D S and omega D omega NS. Omega NS. So we have just found this from free vibration analysis. So what would happen if I account my damped system and then I have to find out my damped natural frequency. So there is no much of the difference between them. Is all because of the values of zeta for the shock absorber. If you see zeta, or if you see that's 0.2 to 0.4 value for shock absorber, and for shock absorber spelling. Shock absorber, and for tire it is 1 order less. It is 20% here, means it will be 2% at the max. So it is insignificant. So that you should understand. So that is why there won't be much difference of this. So we always go with looking at your natural frequency of the system. So you may ask, there is a damping present. How can you take this as a basis and study? Is all because of this design aspect of damping coefficient value or damping ratio that go in your vehicle design. Then see, vibration isolation is concerned. The suspension system is very good in this case. Is all because of wide separation of natural frequency. Wide of natural frequencies. What are the natural frequencies? Omega ns and omega nus. So they are separated by that is why you see that when a vehicle goes over the bump, no, there will be a wider frequency excitation, and first in contact is an unsprung mass that would be set in vibration. So the excitation comes closer to 10 hertz, then what will happen? This would be under vibration and this will not have an amplitude much. So because you get an excitation from here to this. So your sprung mass is excited by unsprung mass. Sprung mass is excited by unsprung mass. So if that is so, if this is set into vibration at 10 hertz, then the energy that enters to the unsprung mass would not create this to vibrate, as this resonant frequency is 1 hertz. That's what we have studied from the transmissibility in our force response study. So this is your one where R is this. So where R is ratio of omega by omega n. So in this case, R is what? Omega n us by omega ns. If that is going to be somewhere here 10, you see that you would have your response goes like that we have seen. And that goes through this 1.√2. It goes like that. So that again going to be controlled by damping in this zone. But otherwise, you see, this is all almost going to be negligible at this. So even if it is at 5, you see, this is going to be very close to the value 0. Here it's log scale. If you consider, it's very smaller value, and here it's almost negligible. So your suspension system and unsprung mass act as a good isolator for your vehicle, and any excitation that comes at a higher frequencies due to road interaction would be nicely isolated. Your sprung mass will have a very less amplitude of vibration, or there is no merely amplitude of vibration. That means it is not that you will not get low frequencies vibration energy comes inside the vehicle. It comes when your excitation frequencies that come from the road is closer to this. If it is 1 hertz, around 2-3 hertz, that cannot be inevitable to enter that energy. As you see that, it may not be amplified, maybe it is attenuated, but you have some energy closer to this zone can enter. That cannot be avoided, and that is where you have other mounts in the seats and so on, where occupants are seated and their amplitude of vibration is under control, and they would meet the requirement of SAE or ISO 2631 standard. So we are going to see them all detailed in our upcoming classes. So with that important note, let us now get into another important step, fourth step, finding out an amplitude ratio considering the road input, right? So step 4. So here the road profile is, I'm going to consider a sinusoidal profile instead of considering random profile. Let us look at that separately in the next class. So I'm going to consider here it is MS, and we'll have KS and CSH, and then your unsprung mass. And here I'm going to consider only the tire stiffness. I will neglect the damping nature of the tire. As you know that compared to that of the damping of this, that is neglected. So I'm not going to consider that for the simplification of our process. And now this is going to be with the sinusoidal excitation. So either sine or cosine function that you can take, and then you see that what is that is going to be here. So this is going to be your Z2, and this is going to be your Z1, and here what you have is Z0. So if this is the excitation, I can now find out the same way. How did we do for an undamped free vibration system? You can substitute the trial solution, and then you can come out with the final answer. I'm going to write only the final answers for the simplicity. We will not do, and that's also not required for an exam point of view, but we need to understand that. So the damping is of the tire is neglected. This is what is important. Damping of the tire is neglected. So neglecting that, I can write my amplitude ratio Z1 by Z0. That's going to be under root of A2 by root of B2 plus C2. So now you may wonder, what are these A2, B2, C2? So this A2 is going to be Ks KTR whole square plus CSH KTR into omega whole square. So look at here, this omega without subscript, that is what is the excitation frequency. So the frequency here, whatever is there, I can vary the frequency of this. So it's not one sine wave. So I can keep varying the frequency of this harmonic excitation, and then I can see my response. So this is my excitation frequency. And we have just now done in step 3, what is its natural frequencies. So having that, I would be able to get my transmissibility and so on study. And here the step 4 is to get what is this amplitude ratio of my sprung mass for the given road input and unsprung mass for the given road input. So for that purpose, this is the equation, and let's call this equation number 17. I just go with the textbook number so that it is easy for you to follow. And B2 is going to be Ks minus omega ms omega square, Ks minus ms omega square into KTR minus mus omega square minus ms ks omega square whole square. And C2 is going to be CSH omega whole square into ms omega square plus mus omega square minus ktr square. So by substituting the values of the vehicle given, and you would be able to get what is this amplitude ratio. So that gives you what is that transmissibility. So if you have a road profile amplitude, is that not elevation of the road profile, and what would be your sprung mass amplitude of vibration. And this is again a deterministic model because I have here my road as an harmonic excitation road. All right. So in this, now what is this omega? What is this omega here? So this omega is what is an excitation frequency. That is what is called the circular frequency of excitation. Of excitation. And how do you get this omega? I know I drive my vehicle with velocity v, forward velocity v, then I would have my omega is 2 pi v by L omega, w. So this is what is called a wavelength of the road. So what is here v is vehicle speed. You can be given a problem where you would be given vehicle speed. So you know what is my excitation frequency in the system. So vehicle speed. And L omega is what is wavelength of the road profile. The road profile. So I mean to say if this is in meters or in mm, so this is what is the wavelength, L omega. So vehicle speed, and if I divide that by L omega, what do I get is frequency of excitation in hertz, and multiply that with 2 pi, I'll get circular frequency of excitation, and that is what is appearing in this equation. So what is that we are doing here is to get this amplitude ratio. This step 4 is forced response study. Forced response study. So step 1 in any vibration analysis is model description. Step 2 is deriving the motion governing equation. Step 3 is finding out its natural modes, finding the system natural behavior. And step 4 is to go in for what is actually happening when it is forced to vibrate. And that is what is that we have taken. For the simplicity, we have neglected damping of the tire in this case. So also we have considered the input as harmonic excitation. Excitation from road. So if we have that, I would be able to have my steady state response, whatever that we have done in our previous study. So the classical method of vibration analysis, I would have my differential equation 1 and 2, where I will neglect my damping of the tire, and I would have my forcing function. And that forcing function when I give is that not is equal to, is that not cos omega t, where that omega is what is this excitation frequency, and the entire thing would be changing. My responses I would consider correspondingly my harmonic response, and then I substitute that in the governing equation 1 and 2, what we have done in the last class, and I would be able to deduce this kind of final expression. Where I would get my amplitude ratio, and these terms are this. So you can see here, I have this omega is what is an excitation frequency. There is no explicit appearance of natural frequencies in this A2, B2, C2, right? That's very clear. So I can make them appearing. If I take Ks out, what will happen? 1 minus ms by Ks. So that's become 1 omega by omega n square all. We can modify that, but I'm not going to do that. and I leave it to you this, and as you take your notes, you take all these formulas may be required while solving the problem. So I can make in this again further simplified in case if I do not consider the damping of my shock absorber also. What would happen? My equation 17 and the other equation also, let me write. The other equation is 18. Equation 18 is Z2 by Z0. Z2 by Z0. And that would be given by A3 within radical square root of A3 by square root of B2 plus C2. B2 plus C2, where B2 plus C2 is same as for equation 17. So this is equation number 18. And you see in this A3 is what is given by KTR into Ks minus Ms omega square whole square plus CSH KTR omega whole square. So this big derivation is not necessary. That would take more time, and rather you can take down these formulas for a quarter car model when it is having a forced response study, considering only the shock absorber damping value. Now, if I neglect the damping value of shock absorber also, then my equation is further simplified. If we take CSH is equal to 0, then it is going to be only the spring of your suspension spring of your equivalent spring of your tire, and with the road interaction harmonic excitation, your Z1 by Z0 is going to be simplified. So you can look at that equation here, A2. So in this term is going to be 0, right? So wherever CH is there, that is only going to be 0, and you can easily rewrite this equation 17 and 18 would become as this. So it's going to be having numerator Ks and KTR, and denominator I would have same B2 plus, yeah.
KTR into Ks minus Ms omega square, it's whole square, right?
One
in
minute.
A3.
Yeah, just a minute. No, this is all whole. Yeah. Is that clear now? Yeah, this is for including KTR. KTR into Ks minus Ms omega square whole square for this. So it is KTR square plus, sorry, KTR square into this square. And here this equation would become, since there is a term of SCH in other terms also. So this denominator is going to be simply Ks minus Ms omega square into KTR minus MUS omega square minus MS Ks omega square. That's my equation 19. So 17 become 19 like this. So your 17 equation would become like this, and 18 equation would become Z2 by Z0. So what is the amplitude of your tire wheel assembly for the road harmonic excitation? The KTR into Ks minus Ms omega square divided by. So in this A3, this term is going to be 0, and A3 under root of A3. So the square goes off, and we have only this. Then denominator you would have Ms MUS into omega N1 square minus omega square into M omega N2 square minus omega square. See, look at here, you have your natural frequencies are brought into this. All right, so this is 20. And what is this here called? When this excitation frequency omega is equal to omega N US, that's called the wheel-hop resonance. Wheel-hop resonance. So the wheel-hop resonance is what is taking care of an isolation that is getting into your vehicle. So when you go on a vehicle on the road surface, the vehicle, you see that the road irregularities can excite your tire wheel assembly. That will be bouncing. But you see, vehicle body would be having less, and that is all because of the energy mostly going in, taken away by your unsprung mass. So the lesser the amplitude that getting to your vehicle, and that is what is going to provide you good ride comfort. That is the default design in passenger car. So this is all what that you could understand from your quarter car model. So it is not necessary that you have to take a full car model and you have to study. You can look at an important motion independently, like a particular model, and then you can study. So ultimately, what is that we are interested in? What is this MS, sprung mass amplitude of vibration? So that is going to be less. That is better design, right? So this all are in a quarter car model. So we have done that in systematic way. Any analysis of vibration should start with again model description, that is representation of mass spring damper system, and then deriving the equation of motion by applying Newton's Euler equation. If necessary, pitch and bounce model, you see that we are going to have a moment balance. And then number 3 in any analysis, looking at its natural behavior. So that's what we have done in first hand. And then we will do a response study for the forcing function. And that is how we will end our analysis, right? So what is that understanding now? As I increase my degrees of freedom more and more, that system is going to become more complex. So if I have to take my full car vehicle model and if I have to do this deterministic analysis is easier. Random excitation analysis is a bit involved, that we are going to see in a third part of our ride dynamics portion. When you have to account the road surface irregularities. I am not accounting road surface irregularity. I am considering the proving ground road. Like I have durability test of my vehicle is done on a road profile which is sinusoidal. So if I ride on that, what would be the response, the worst case measurements that I am looking at it. And those are called a deterministic model. But my road is flat road and asphalt road, it is very smooth. When I drive my vehicle, and how I would characterize my road, because the asphalt road of highway is not necessarily all the time of very smooth. There can be a lot of discontinuities. So how it is all accounted is what we have to see, and that's where you see the random vibration basics to be learned. We will have that separately. Maybe I will teach that on the next week. So this week task is another 20 minutes also. We will look at another interesting 2-degree freedom model called the pitch and bounce model, or bounce and pitch model, either way it can be called. And we will do in Friday's class what are the different standards that are there going for understanding human perception. That is the second objective of ride dynamics. And in Monday class, I would teach you this random vibration road characterization, and that is going to end our module 2. That's all. We are not going to have much more. And of course, the suspension aspect of design we will look at in a separate module in our ride dynamics, right? Yeah. So with that, let me just now continue with lecture with another interesting model called the pitch and bounce model.
Excuse me, sir.
Yeah.
Sir,
Yes.
for the last equation, Z2 by Z0.
Yeah.
Sir, the denominator is different as Z1 by Z0, but in the equation it is root B2 square plus B2 plus C2. Sir, why it is there?
1 minute, let me just look at it. Where? Here. This one, number
Yes,
20 you are asking, right?
Yes, sir.
Yeah, so B2 plus C2. So look at B2 and C2, what are those you see here? I have B2 here is this, and C2 you see CSH, that falls. So we are neglecting the damping of our suspension. So this entire term goes off. So it is simply under root of B2 only would be existing. C2 becomes 0, right? You understand? The C2
Yes,
values
sir.
here.
But Z2 by Z0, we can see that it's different from the first one. Means For Z naught also root
I have
B2
two sets
will
of
be there. No?
I have two sets of equation you have to see here. 17 and 18 one set, and 19 and 20 another set. So 17 and 18 is considering the damping neglected only for the tire that's existing in this diagram. So I do not consider the damping coefficient for the tire. That's because it is insignificant compared to that of the damping of the suspension. So it is very clear. So in that C2 is accounting, you see the damping coefficient of the shock absorber. Clear? Is it clear or not?
Yes, sir.
Yeah. And in case if I do not consider even the suspension shock absorber, right? What would happen? Yeah, I know that my vehicle is going all the time on a very smooth surface only. I will not have any potholes on the road. Like ideal case, if I consider, I don't require actually to control my amplitude. I know my excitation will never come closer to the bounce frequency of vehicle body. If you consider like that, what would be my amplitude? So I'm going in for having an undamped force vibration. This is undamped forced response. So when it is undamped force response, I would have in B2 and C2, B2 term does not have the coefficient that comes from the suspension, whereas C2 has, that's disappearing. Is it clear? That is why I have my equation 20, only this comes. And here, you understood what is that? Is that your doubt or anything else? Is that your doubt or anything else?
Sir, what is omega n1 square and omega n2 square?
You tell me. After all teaching you, you are asking what is omega n1 square. That is what I was telling you here. It's explicit appearance of your natural frequency of sprung mass and unsprung mass. Though you are looking at Z2 by Z0, you see that is having an influence. So your doubt, I understood what has happened to this term here, right?
Yes, sir.
This term. Why do I write this as a homework you can work out? Either putting this term over here or writing this term is one and the same. And you see in one case, I purposely put in one case, you do not have an explicit appearance of natural frequencies. On the other case, I have it, they are appearing. So they are equivalent, this denominator, all right? Okay, you can just work out and see. Do I answer your question? See, I had to go to the next topic.
Yes, sir.
Yeah. Yeah. Good. It's a good critical observation. I appreciate your thing. Please work out and see they are going to be one and the same. I just have put in one equation, 19 equation denominator without an explicit appearance of natural frequency of sprung and unsprung mass. On other one, you can do some manipulation and then that's going to be expressed with those natural frequencies and excitation frequencies together. So now let's get into pitch and bounce model. Maybe I would describe this model, and solving this model we will continue if time is going to be a shortage, right? See again, let's look at a vehicle. So this vehicle has got now here spring, and this is seated. So let me just draw a schematic diagram of my passenger car. And say this is the location of CG, and you know something called wheelbase, the dimension wheelbase. No, so this is what is called wheelbase. Front axle tire contact point to rear axle tire contact point is what is called wheelbase, given by letter L, and that would be separated by distances L1 and L2. So where L1 is CG location of your vehicle from the front axle along longitudinal direction, and L2 is the CG location from the rear axle along the longitudinal dimension. So this is L1 plus L2. So what is wheelbase? L is equal to L1 plus L2. L2. So this is going to be always there with you, and many of the occasion you will see. And we know the convention that we follow here is this is forward direction, and we follow SAE coordinate system. So I would have my right hand, three fingers are stretched in this fashion, thumb is pointing down. So I would have my positive X direction, forward direction of vehicle, positive Z direction is downward, and positive Y direction, lateral direction is from left to right. So this is the coordinate system. If I consider, I would have here this vehicle body is seated on this spring. So I have these two springs. I don't model now here an unsprung mass. I will not consider an unsprung mass. You know, the reason is the wide separation of natural frequencies of the sprung and unsprung mass, right? Makes that the vibration of your vehicle body is independent, and unsprung mass is independent on its natural modes. So sprung mass, the natural frequency is not going to excite this, or this is not going to excite this. So I can make these two vibration independent. So I would neglect an unsprung mass in my model. I would take only the sprung mass, and that sprung mass is now at its static equilibrium position. So what I mean by static equilibrium position, this sprung mass seated on the suspension spring. So this is front suspension spring KF, and this is rear suspension spring KR. So this is seated, and then it is resting on its static equilibrium position. So this is my reference. So from this reference, I am going to have my two motion. One is the linear translation of CG Z. Another one is angular motion of my vehicle body about CG, and that would be positive in this direction, clockwise direction, as Y axis is here. So the moment here is positive in this direction, and downward direction is positive. So this is what is the oscillation that I get. If I say it's an oscillation, this is pitch motion, and this is bounce motion up and down from static equilibrium position, right? So this one is what is pitch motion, and this one is what is called bounce motion. And now this model is described by this diagram schematically. I will have my this line. So I will represent a line to represent my vehicle body, and that has been vibrating from its static equilibrium position. So static equilibrium position, I would have that comes down below here. So it has come down here from this y distance Z, and I would have my vibration of the system like this. So look at this now. So this line is what is referring to my, so this wheelbase L is what I'm taking. So that well is what is now here. It's displaced like this. So displaced by an angular displacement theta, and that would be here theta and here theta, and this distance is Z. So what is this distance from mean position? So I have to measure these distances from the mean position. So this is the distance, and this is the distance here. So this distance is what? Z minus L. This is now it is CG. It's CG location, right? CG location. So this is L1 and L2. So this portion is L1. This portion is L2. So I will have here this displacement is Z minus this length, and that's going to be Z minus L1 theta. Z minus L1 theta. And here it is Z plus L2 theta. Is what is this distance altogether. And you can imagine that this is on this spring. on the spring. And here the spring is Kf, suspension spring rate of the front axle, and suspension spring rate of the rear axle. So if I have here one spring and the other side, right side one spring, then equivalent addition is what is this Kf? Front suspension spring, rear suspension spring together. So now you know that the free body diagram here, the forces of this, the spring force would act upward, because that would be bringing this always to the reference location, which is our static equilibrium point. On the other hand, you see this entire thing is controlling its motion. To apply the Newton's equation, I'll have to take the same diagram where it is subjected to mz double dot and I into theta double dot, right? Because it's rotating also. The motion is general plane motion, like that. Your mechanics you have studied. So it is addition of your pitch and bounce together. So pitch is referring to an angular oscillation. Bounce is referring to the translational oscillation. So your free body diagram here on the vehicle body. So this line here represents your vehicle body, and these are the springs. And you see there is no damping, shock absorber I consider here. So this analysis now is only for its natural behavior. Natural behavior to predict. So it is for its free vibrational study. Natural behavior means it's free vibrational study. So I'm not going to excite with harmonic excitation and so on. So I'm just going to excite disturb the system from its static equilibrium position, and it is going to be. And why is this called 2-degree freedom model? 2-degree of freedom model is all because of there are two independent coordinate theta and z, and they are coupled together. So the pitch and bounce model is a coupled model. What do you mean by coupled model? If one place that excitation comes, that excitation would create both translational oscillation as well as rotational oscillation, and that is why it is coupled model. It is. So you can decouple it. Once you write the equation, you can go for a specific case. If pitch and bounce to happen independently, they are not coupled, what is the condition? All you can dictate it once you start deriving the governing equation and proceed with this, right? So this is my free body diagram now to derive my governing equation. So let us write the governing equation carefully. So on one side, I have it here, this. So my convention is what? Down positive, clockwise moment positive, right? So now this forces, two spring forces are upward, right? So that's going to be negative. So I'm going to have my forces on one side minus Kf into the displacement here is z minus L1 theta minus Kr into z plus L2 theta. And that's what is equal to, here it's down, so plus mz double dot. So what is my equation? So this m is here sprung mass. So unsprung mass is neglected. Unsprung mass is not accounted. The reason for not accounting unsprung mass is the frequencies are well separated, and you can consider the motion of body independently. Because the excitation that comes from how the body is excited, it's because of your unsprung mass. But the unsprung mass is having its wheel-half resonance at 10 hertz. So the amplitude what is entering the body is very less. So I'm making that as an independent entity. So I just look at my vehicle body with only the springs of the suspension, not accounting unsprung mass and the tire wheel assembly property and so on. That is what very carefully to be understood. That's why it's Kf and Kr alone, which are coming from the spring stiffness of your suspension. And so this mass is ms, sprung mass alone. So put the subscript ms here. So my first equation is going to be ms z double dot this goes on the other side. So it's going to be kf into z minus L1 theta plus kr into z plus L2 theta. And that's what is going to be 0. That's my equation number 1. You see here, I have z and theta combined. So when I have both of them are appearing here, that's why it's called a coupled motion equation. So now let's continue to get another equation taking moment about CG location, right? So what is that I get? Kf into L1. So this angle I consider is very smaller angle. So let me consider this force here, whatever that I have is multiplied by L alone. So I would have here on this side it is Kf forces spring force Kf into Z minus L1 theta, that's spring force, multiplied by L1 is what is I'm considering linear model. That's why this theta is very small. When I consider, I can just make this approximation. It's just multiplied by L1. So this force into L1 is now what direction? Clockwise. So this should be positive, and minus kr into force Z plus L2 theta into L2. Why minus is because this spring moment about this is counterclockwise as per this SAE coordinate system, that is minus. On the other side, I have my rotational moment, unbalanced moment, that is going to be that is like an effect force, effect moment is I theta double dot, where I is mass moment of inertia. Inertia of body, vehicle body about y-axis. So how do you get I? That is going to be ms into ry square, where ry is radius of gyration. So you understand this all fundamentals that you have studied in your properties of rigid bodies in engineering mechanics module 4. So you cannot just forget them, right? So that's quite useful here. So this is what is my second equation. So let me rewrite this equation once again and get. So this I will put subscript y so that it is about to y-axis to say. So Iy into theta double dot, and this goes on the other side. So it's going to be minus kf L1 into z minus L1 theta plus kr z plus L2 theta into L2 is what is equal to 0. That's my second equation. That's my second equation. Right, so here I'm going to introduce or group them. I'm going to group them. So again, let me write this equation, grouping z and theta together terms. So this one equation is going to be ms z double dot plus I have here kf and I have kr positive. So kf plus kr into z. And see here theta common. So kf into L1 minus and here kr into L2. So let me write here plus kr L2 minus k1 L1 into theta equals 0. So that's my equation 1. And equation 2, once again, I'm rearranging. That's going to be Iy theta double dot and plus. So here again, z terms I have to look at. That's going to be kf L1 minus. Here this krl L2 positive. So it's going to be KRL2 minus KFL1 into Z plus, if I multiply inside plus KFL1 square. So KFL1 square plus, here it is KRL2 square into theta, that's going to be 0. This is my equation 2. So this is interesting, right? Why do I write this? Is again, I'm going to simplify my equation so that that's going to give you some kind of insight and easy handling. I'm going to take now Z double dot. I'm going to write my expression of single degree freedom system. You've seen, right? What is that? Mx double dot plus Cx dot plus Kx equals 0. I rewrite this as x double dot plus C by M x dot plus K by M x equals 0. So in this, for an undamped system, this is going to be 0, then it is going to be x double dot plus K by M is nothing but omega n squared x is equal to 0. If undamped. This is all for what? The single degree of freedom system we have studied in first module. So in this form, the coefficient of x is what is omega n squared. So I'm just going to write like that so that I will know what is my natural frequency for bounce and pitch that I'm wanting to get it. That's why I do this kind of thing. So I divide this equation 1 by ms. So it's going to be this plus, I'm rewriting here this kf plus kr by ms as d1. Is that plus kr L2 minus KL K1 L1 by ms as d2 theta equals 0. So here I know where d1 is kf plus kr by ms, d2 as KRL2 minus K1L1 by ms. Right? And the second equation is going to be theta double dot.
Excuse me, sir.
Yeah.
Sir, it is KRL2 minus KFL1.
KR
L2
L2
minus KF.
KF. Yeah, it's not K1, sorry. Thank you. KFL1. Correct. This is KR. Is that clear? Is it correct now?
Yes, sir.
Yeah. So theta double dot, and here see now I'm dividing this by Iy. So if I divide that by Iy, I would have this term as D3, let me call, into Z, and this is going to be plus, see this is same as D3, and this is going to be, let me write D2 by Ry square into Z. So this is theta, I'm sorry, this is theta into Z equals 0. So see this coefficient, theta coefficient divided by ms is what is D3. So what is D3 now is going to be kf L1 square plus kr L2 square divided by Iy is what is D3. And here when I divide by Iy, I have here this term by Iy is ms Ry square, that ms goes off, ms to come here to accommodate D2. So these are my set of equations. So in this, if you look at, interesting it is, right? Look at this D2 term, D2 coefficient D2 that's present here and D2 present here. If this D2 happens to be 0, what will happen? This term goes off and I'll have Z double dot plus D1 Z is equal to 0, which is similar, something similar to this. So D1 is going to be my bounce natural frequency. Right? And here it is going to be D3 is what is my pitch natural frequency. That's why I just rewritten this and define D1, D2, D3 for our convenience. So,
Sir, what is R square?
Ry is radius of gyration. Ry is radius of gyration. You know what is the radius of gyration, right? You have mass moment of inertia. That is the virtue of resistance for any rotation. That's a property of rigid body for rotation. So your rigid body entire mass is shrunk and kept from the point of rotation at a distance. That will not change your Iy value, and that point is what is called radius of gyration. So I would be, Iy is defined as ms into ry square. Like I is equal to mk squared formula you have seen in your rigid body mechanics course for a disk rotation or for a plate rotation or for bar rotation about it. So all those formulas that you have seen. So in this case, it is the vehicle body rotation about its y-axis, and the mass moment of inertia is what is the virtue resistance, like mass for translation. This one is for rotation, and that is defined by this. So that is this Ry. So this Ry square term comes because I divide this by Iy. So D2 you see here there is ms. So that term goes off ms, and ms is taken with the numerator to write D2 in this. So now D2 is what is called coupling coefficient. Is what is called coupling coefficient. See, if this coupling coefficient is not present, it is going to be an independent motion. What I mean by that, if I apply a force at CG location, it will only bounce. If I apply a moment, then it will only have pitch motion. And that is not preferred. That is not preferred. Correct? If this D2 is 0, then it is uncoupled. Equation. Uncoupled equation, which is going to be a poor ride. So the ride condition is not good. So you require a coupling term. And the design of your vehicle is that if you have an excitation at one wheel, that is going to excite your body with both bounce and pitch. And they would get an addition of your bounce oscillation and pitch oscillation together. So this is all now to look at what would happen, why it is poor quality, poor ride, all you can understand. The moment I make it now, we'll go into physical aspect later. When I make D2 0, what is my D2? This is the term, KR-L2 minus KF-L1 by MS equals 0. That's what is D2. So when I say this is equal to 0, that says KR-L2 is equal to KF-L1. So this is not preferred, not a good design. Not a good design, right? But if this is the condition, you see these equations is going to become two single degree freedom equation, and but these two equations is going to become what now? Only z double dot plus d1 z, that's equal to 0, and theta double dot plus d3 theta is going to be 0. So these are the two governing equations. So now in this, you know what is d1? So d1 is bounce natural frequency square. Frequency. So root of d1 is going to give me bounce natural frequency, and root of d3 is going to be pitch natural frequency. So d1 is what is that? You have ks or kf plus kr by ms. So that's going to be bounce omega z, omega n z. That's going to be under root of ks plus kr by ms, and this one would be omega n theta, that's pitch natural frequency. That's going to be d3. So d3 is what is this? So kr. What is d3? Kf L1 square. Kf L1 square. Kf L1 square plus K2 L2 square by MS R5 square. So this is going to be my pitch natural frequency for an uncoupled system. So you can be given a vehicle data and you are asked what is bounce natural frequency and pitch natural frequency. When the system is uncoupled is this. When the system is coupled, how do you find its natural frequency? And then amplitude ratio, there's something called the concept of oscillation centers and so on. That we will see in the next class on Friday. And we will continue with that human response for vibration also on Friday. Right? With that note, let me stop today's class. If you have any doubts, I would answer. Otherwise, we will end the lecture. Do you have any doubts?
Excuse me, sir.
Yeah.